they can ask you, like, let us suppose a dipole is given. This is minus q, this is plus q, right? And they ask you, you have to find the potential at this point P, right? And from the center of this dipole, right? So let us suppose this distance is r. This is L and this is L. So a dipole system has been taken. This is minus q plus q. You have to find the potential at point P. So the expression of that is Vp is equal to Kp upon r square minus L square, right? So this expression is also important. There is a proof. I don't think so. The proof is required to be taught to you. Yeah, you know everything. So you have to find, if they ask you, you have to find at a certain point which is lying along the axis of the dipole. This is the formula. Now, what about when it is a very small dipole, like r is much greater than L, right? Then you have to substitute L square is equal to 0. Then you will get the potential at point P as Kp upon r square, right? The same was in electric field. Electric field we had to find at the axis. That was the formula 2Kp upon Rq, right? So these two formula is important. Now in electric field, we have to that the direction of E and P is same, right? But in this case, no need to consider about anything about the direction, right? It is a scalar quantity. Then at the perpendicular bisector, they can also ask, this is minus q and this is plus q, and they tell you find at this point P, right? Which is lying at the perpendicular bisector of this. Then what will be the potential at P? So at P, that will be due to, let us suppose this is 1, this is 2, right? So that will be V1, right? You have to find the potential due to this V1 charge, that is minus q, and due to this second charge, which is plus q. So that is V1 plus V2. And what is this V1? For this point, you know it is lying along the along this axis. And what is the length of this? So this is L, this is R, so this is R square plus L square, right? So the potential at this becomes KQ upon R square plus L square. And what about this? Due to this charge, what will it be? This will be also same. The distance is same, right? So R square plus L square. And we know the summation of this and this is equal to 0. Why? Because if we take a plane which is lying along this axis, right? So this is an equipotential surface, right? Whatever may be at whatever point you take, the potential will be same because the distance from this charge and this charge is same, right? So obviously that resultant potential at this point P becomes 0. So along the axis there is an expression, but along the perpendicular bisector, the potential at that particular point is 0, right? So one more thing they can ask, let us suppose this is minus q, this is plus q, and they tell you to find it at a certain point P, which is r theta, right? The same thing what we had done, right? What was that? We have to, if this is the direction of the P, we have to resolve into P cos theta, and this as P sin theta, or perpendicular by, right? P sin theta. So electric moment, that is now resolved into two components. So the resultant at the point P will be Vp cos theta plus Vp sin theta. And we know this cos component is lying along the axis. So it is Kp cos theta upon r square. And this is lying along the perpendicular bisector, which is equal to 0. So finally, you are getting this expression, right? So they can ask you some problems regarding this too also, right? Then there is also very important, like what is the relation between E and V, right? So let us suppose this is the electric field, yeah? And there's a charge Q here. You have to find the potential at this point, and this point, right? And you can say, let us suppose this is 1 meter, this is 2 meter, this is 3 meter. So what happens if you have to find at this point, you know it is KQ upon R, right? This one KQ upon 2, this KQ upon 3. So what is happening? We see the electric potential is decreasing, right, along the direction of the electric field. So that's a very important relation. That is, the potential, it keeps on decreasing as you in the direction of the electric field, right? So as you can see, it is going on decreasing, right? So this concept is also used in some of the problems they can ask you, right? Then the relation between E and V and the V, that is also important. So if let us suppose this is a uniform electric field, right? And there is a charge. Sorry, this is the uniform electric field. And you are moving from point A to point B and you're doing some work, right? And the distance is, let us suppose this is a R vector, position vector, right? So now VB minus VA will be equal to minus of the electric vector dot R. So this is a very important relation. That is, the change in potential is equal to minus of the electric field vector dot R vector. So the dot means you have to consider this angle between E and R always, right? So, or you can say, let us, if the distance R is decreasing, right? Let us suppose we have reduced it, A and B, we are reducing it to very a small distance. Let us suppose dr. Then you can write this as dV is equal to minus E dot dr, right? So, or you can consider the magnitude delta V is equal to E dot R vector, right? So this relation is also very important. So this is the relation when the field is uniform, right? When the field is uniform, the relation between the electric field vector and this is delta V is equal to the E dot R vector, right? But when in case of non-uniform field, in non-uniform field, the approach is different. You have E is equal to minus dV upon dr. This is the relation, right? So they can give you like E, they can give you a vector form Ex I cap plus Ey j cap plus Ez k cap. So they can tell you find the Ex component, Ey component, the Ez component. So under that case, you have to like Ex component you can find when you partially differentiate the potential with respect to X, right? When you're doing this, Y and Z is constant, right? And when Ey is when you have to do the partial differentiation of the potential, right? Provided X and Z are constant. And the last one is when Ez you have to find, you have to differentiate partial differentiation with respect to Z provided X and Y are constant. Yeah. So often they have asked, like they either they give you the E vector or they tell you to find it, Ex, Ey, Z. They can also ask you such kind of problems. So you should know where to apply the formula. This formula is for non-uniform field, yeah. And for the uniform field, it is the E vector dot the R vector, right?